Everybody. So today we are going to discuss about time series models. So in the past you have seen neural networks, convolutional neural networks, recurrent neural networks, right? So today we are going to discuss about time series models. So first of all, what is time series? You have to listen carefully. You listen to the sound. So this is the audio for this sound. This is the spectrogram, magnitude spectrogram for this sound. So you saw a drum being played. The drum was played and then corresponding waveform looks like this. This is a time series. So what do you see? The waveform is not just independent. So let's take one sample in this waveform. It's not independent. It depends on so many contextual things, right? It's a decaying periodic signal or something like that, right? Okay. The question is, how do we model these kinds of data? One approach is we take the whole model the whole time series as a vector, right? And make a model which understands this vector, either takes as input this vector or gives as output this vector. But then the problem will be that any slight shift in this vector, let's say this drum started at t equal to 0 versus the drum started with few samples delay, it will be totally different output or input, right? So these are the challenges which need to be dealt with. So we're going to discuss about Markov models, which I would say are the simplest way to understand time series or dynamically evolving data or data which evolves with time. Dynamic means changing with time. The reference is the book PRML, section 13.1. The chapter 13 is all about sequential data, and this Markov models is discussed in the first part. Now, what are the examples of sequential data or temporal data or time series? One is you have some sinusoid and you're sampling it, right? Maybe a fan is rotating or in a motor, the shaft is rotating, just measure its angle. Those measurements give you a time series in time, right? You're sampling in time. Weather recording, right? In real world, where do you get time series data? In weather. Let's say, what is the temperature at 1 p.m. today, temperature at 2 p.m. today. You open your Google weather forecast, it tells you what will be the rainfall tomorrow at 12 o'clock, 1 o'clock, etc. Right? So forecasting the weather or analyzing the weather, it's all time series. The weather is basically weather measurements or weather data is all time series. Speech, as you saw the example, you have a drum playing. It's a time series of samples, let's say. Videos, any video is a series of frames. Each frame is like an image, right? And from there you can do so many analyses, or you can also generate videos. Okay, now I'll give an example here. Let's take an example of a regression problem. It's a simple regression problem. Look at the temperature on previous days. Let's say you have data from past 2-3 years, and look at all that data and predict the temperature tomorrow at a particular time, let's say 2 p.m. Let's say tomorrow 2 p.m. what will be the temperature? And you have the data for all 2 years temperatures in the past. So how do you model it? How would you model it? One approach could be you take temperature at today, let's say call it T1, temperature yesterday, T2, and so on up to T, or call it as T, today is, let's say, N minus 1. Oh, day N is tomorrow, so today is N minus 1, and N minus 2, so on up to T N minus some capital N. Take all this, put it in a neural network, and predict Tn. Right? Take all the past 10 days, let's say, or past 20 days, 2 o'clock temperature, and feed it into your neural network and give as output Tn. This could be one model, right? What kind of model is this? It's a it's a simple regression model. So it's a simple regression model. You look at the previous temperatures and just predict the temperature tomorrow. Another approach could be probabilistic approach, where you are not telling me exact temperature tomorrow, not a point estimate, but a distribution. Tomorrow the temperature will be of this PDF. The simplest PDF is, louder. Just be confident. Multinomial distribution. Very good. What else? Normal distribution. What else? Uniform distribution. What else? So all these are meaningful distributions. Now, let's pay attention to what kind of random variable is temperature. Continuous or discrete? Continuous. So can I use multinomial distribution to model continuous random variable? No. Can I use Gaussian? Yes. Continuous variable can be modeled with a Gaussian distribution. Uniform distribution? Yes. Right. So all these are continuous distributions are all possible here. Today we'll discuss also about how do you model continuous random variables with discrete random variables. Basically continuous data with discrete random variables. That is also coming on the way. So you can even use multinomial or binomial or it's called Bernoulli distribution to model this data. But let's take simple example, Gaussian distribution. It's a continuous random variable. So let's say P, Tn given all that past readings can be modeled as a Gaussian distribution with mean mu and variance some sigma square, right? And this mean mu and sigma square are estimated from the data or from the past data. So I'll just elaborately write it. It's the same problem. Deterministic model could be a recurrent neural network where T is a function of all the previous readings. Or it could be a linear model, like this one is a linear regression model, and this F could be a non-linear model, right? This F could be a non-linear model, whereas this is a linear regression model. And the probabilistic model, as I discussed, that you can say my Tn distributed normally, where mu and sigma could be functions of past data. All this past data. So this mu is a function of past data. Sigma is also a function of past data. So you made a neural network which predicts mu and sigma. It does not predict one temperature, but it predicts the mu and sigma of the Gaussian distribution, which the temperature is assumed to follow. Understood? But you can use many other distributions also, not just Gaussian. It could be any distribution. Okay. Now, the question you may ask is, once you have a learnable model, how many unknown or learnable parameters are there in the model, right? How many weights are there, biases are there in your models? Let's say in this first model, what's the answer? The linear regression model. How many? K plus 1, Yes. And when you use neural network, let's say mu is modeled with a neural network with n number of parameters. Sigma is modeled with a neural network of some n dash parameters. So n plus n dash is total number of parameters. That's easy. Now let's come to Markov models, some probabilistic modeling. Markov model, okay. The first equation, P of x1 so on up to xn can be written as P of xn so on up to xn minus 1, and this n you can basically take a product over all n's from 1 to capital N. Do you agree with this formula? What assumption is involved here? What assumption is involved here? Independence of data? Anybody else? Huh? IID data? Identically and independently distribution? This is what you're saying? Somebody said only independence? Anybody else? Yes? Be confident. Just say anything. Okay, thanks to those who gave answers and they are very brave. Those who did not give answers, I would expect next time you should give answers. So my answer is that none of these. This is simple product rule. There is no assumption involved. This formula is valid for non-independent samples also, and it's valid for non-identically distributed also. Let's say P of x2 given x1 is Gaussian, but P of x3 given x2 and x1 is maybe Laplacian or uniform or something, right? So there is no assumption involved here so far. So the first line is the general chain rule. Okay, clear? Let's now come to this one. Here there is an assumption involved. What we have done is we have said that P of xn given xn minus 1, xn minus 2, so on up to x1, that thing is reduced to simply P of xn given xn minus 1. We have removed the dependence on the xn minus 2, xn minus 3, and so on. So we are saying that P of xn given xn minus 1, xn minus 2, so on, this thing is equal to P of xn given xn minus 1 only. This is an assumption. This assumption is called conditional independence, right? Conditional independence. My xn is independent of xn minus 2 given xn minus 1, right? So my in this case, so my let's say x4 is independent of x2 given x3. Do you know this graphical notation? Okay, so graphical notation means, let's say in general I would say, let's say I have P of x2 given x1 into P of x1. Then I can simply write it as this is my x1, this is my x2. So this graph represents this formula. It simply says start with the tail, start with x1, P of x1, this part, into this one, P of x2, wherever the arrow is coming from, put that as a condition. So it's x2 given x1, right? Another example is, let's say x3 Can you tell me the formula? Oh, yeah, can you tell me the formula now? What will be the formula for this graph? Yes. Okay, take your time and then raise your hand.
P of x3 into P of x2 given x3, P of x1 given x3.
Very good. So it's P of x3. That is the independent node, you can say, into P of x2 given x3 into P of x1 given x3, right? Uh, the general most thing would be written like this. The general most means where there is no assumption. Here there is some assumption involved. General most thing will have this branch also, or this arrow also will be there. This would mean P of x3, x2 given x3, x1 given x2, x3. That is the most general thing. But here we have removed this connection. By removing this connection, we made it something, some assumption basically we have uh, incorporated into this model, right? So by removing the connections, we are adding assumptions, right? Now you look at this one, the most general form. Can you write the most general form for 4 variables, x1, x2, x3, x4? What will be the most general graph without any assumptions? Can you draw? You can come in the front. There are so many seats vacant here. All can come in the front. There is no uh, problems. Okay, now tell me what is the most general form, uh, what is the most general graphical representation for 4 random variables, x1, x2, x3, x4. Just draw it on your notebook. Done? Yeah, I think many of you have given correct answers. So this would be simply x2 will depend on x1, that already is there. X3 will depend on both x2 and x1. Here only x2 dependence is shown. So there should also be another dependence from x1. And x4 will depend on all three of them. Only one dependence is shown, so other two will also be like this. Oops. That's it, right? So now you see that we have removed three arrows to make it a first order Markov chain, right? So Markov chain basically is a simplification by reducing the model complexity, by making assumptions that dependence is not very long, it's only to the immediately previous node, right? That's the first order Markov chain. The mth order Markov chain in general will say depend on past m inputs or past m nodes, sorry, in the time series, right? All of you understood the graphical notation as well as the mathematical representation, that p of x1 so on up to xn in general is written as p of xn given n minus 1 so on up to n minus capital M, and you product over all n. All right? All n, yes. Yes. Why are the arrows shown? It could be either way. No, p of x2 given x1 is not same as p of x1 given x2. So to make it clear, we show arrows. Okay, now a question for you. Given a factorization, p of x2 into x2 given p of x2 into x1 given x2 like that, given a factorization, do you have a unique graph or it's possible to have multiple graphs? That's a question for you. Think about it and give me the answer in next class. Okay? Do we have unique graph or is the graph unique? For a given factorization. Okay, so that's a question for you. Okay, now let's see. First order Markov chain. Probability of temperature on a day n, it basically depends only on temperature at n minus 1. Does not depend on the past temperatures. That's a simplification, may not be correct, but this makes our model very, very easy to understand, easy to learn, easy to do analytical analysis, right? So that's how it looks like. That probability of temperature at on day n depends on only n minus 1, n minus 1 depends only on n minus 2. So in this way, the whole thing is. Similarly, you can say rain of on any day can be modeled in a similar way. Okay. But the question you may always ask is, are they really independent? Temperature today, given temperature yesterday, is it independent of all past temperature record? So the answer is no, it need not be, huh? So I will give you an example here. This is just a model. Every model is wrong, right? You know that, right? All models are wrong, but some are useful. So these are very useful models, but they are wrong. All models are wrong, basically. Okay, now I'll give an example of long-term dependency now. Let's assume every word is like a token, huh? And it's a PDF of this word given the previous words. How will the PDF look like? What are the possibilities you can fill here? Basically, it could be anything, right? It's very wide scope. Could be anything. लड़की ने अध्यापक से पूछा राम कौन है, श्याम कौन है, कानपुर कहाँ है, भारत की राजधानी क्या है? So many questions are possible. Now look at a little longer sentence. लड़की ने अध्यापक से पूछा क्या मैं घर जा हाँ सकती हूँ? Majority said सकती हूँ, right? So you see the PDF has changed so much. Options have become so limited. Now, क्या मैं घर जा सकता हूँ? That is omitted. Why? Why is sakta is not an option here? Which word is influencing it? N minus 1, 2, 3, 4, 5, 6, 7, 8, 9. N minus 9. is influencing it. So there are long-term dependencies. If you simply use first order Markov chain, can you model सकती हूँ that सकती हूँ is more probable than सकता हूँ? That dependency will never come if you have only first order Markov chain, right? So that's why we need to use longer dependencies. So one needs the context from the past and very long context. Okay. Now the question is, how do we model long dependencies? Why people use Markov chains? They are very easy, right? Your complicated PDF has become simply a chain, a linear chain, right? And when you do analytics, means you try to solve the equations, means optimizing, etc., or inferencing with your hand or just on notebook, Markov models are so easy to deal with. Just like Gaussian PDFs are so easy to deal with as compared to other complicated PDFs, right? Because analytically easy to differentiate, easy to integrate, very simple terms, things like that. So now the question is, how do we model long-term dependencies? I don't want to use simple Markov models because they are too limited. Simple first order Markov models, they are too limited. What can we do? One possibility is that make your receptive fields very large. In other words, how does it translate to the language of Markov models? What is the meaning of this? When I say very large receptive field or input or dependency, what does that mean? What are we doing to the Markov chain? Higher order Markov chain, right? Use not m equal to 1, but m equal to a very large number. So that's how you can make long-term dependencies. Another smarter, but the limitation here is that if m is large, then your equations become dirty and it becomes difficult to learn. A very smart way to deal with this problem is use latent variables. Use latent variables. Uh, I'll give you an example, just a very crude example. Go back to the previous slide where we discussed लड़की ने अध्यापक से पूछा क्या मैं घर जा dash, right? So whenever every word is coming, you keep a notebook with you. In that notebook, you keep some parameters and keep updating them. Let's say gender of the there is something called subject, object, right? Instrument, all those cases are there. So let's say subject. The moment you saw ladki, you make it, oh, subject is a female. Then ladki ne. So ladki ne matlab ki this is a subject who is a female subject. Then adhyapak se, oh, adhyapak could be, it will be a male. It's not adhyapika, it's an adhyapak, it's a male teacher. So in your notebook, you just updated some parameters. What are these parameters? You have predefined, okay, in this case. Okay. Now when you come to this final word, ja dash, now sakta will be not possible because the subject is female, right? So basically, you're trying to keep a notebook. Now, in our language, in our statistical language, we call that notebook as a latent variable. A latent variable which stores the relevant parts of previous information and just uses it to do predictions. So there are two ways we have discussed in this course, or we will be discussing in this course. One is the recurrent networks, which you have already seen. The other is the hidden Markov models, which we will discuss later in the course. What are recurrent neural networks? You have seen it in the past, in the previous videos. I'm just revising briefly. It's a model to process sequences. It has memory, just like autoregression in signal processing. Where is the memory? You have an extra latent variable called h, or a hidden variable, or a hidden node, or a hidden vector h. So h depends on x, and h depends also on its previous value. Like ht depends on xt, the current input, and it also depends on the ht minus 1, the past input. So your notebook, when you're updating your notebook, it depends on the past notebook state. Let's say in the past, your notebook said the subject is a female, and then in the next time instant, you said, yeah, the subject is female, but then the object is male. You just updated it, right? So it depends on the past state of your notebook. It also depends on the current word which is coming, like adhyapak ne, the new word which is coming, or the new input which is coming. So HT is basically that notebook or that latent variable, and it depends on XT and HT minus 1. Is this clear? This is a linear representation. It could be nonlinear also. You can put some ReLU or softmax or sigmoid or something. And your output YT depends on HT, right? Your output depends on the latent variable. And graphically, it's like this. Do you agree with this? This graph you have seen in the past. It's a simple recurrent network. Now, one thing you can note here is that these W's, the W1, W3, they are independent of T. That's the nice thing about recurrent networks, time series models, huh? That your model is independent of time. How many of you have read LTI systems? LTI systems? They're time invariant, right? So these are also time invariant models. They are not linear because we have nonlinear layers, nonlinearities, but they are time invariant. That's the good quality which they retain. And in general, you have seen in the past lectures that this is how the recurrent network looks like. You have some nonlinearity applied to the UXT plus WHT minus 1 plus B. F is some nonlinearity, ReLU or sigmoid or something. And then your Y output is, let's say if it is a categorical output or a multi-class classification problem, then you will simply say it's a softmax of HT, the current state of your hidden vector. Clear? Okay, now these are all theoretical tools which you can use to solve your problem. What's your problem? This is your problem. Huh? You want to model audio, which is a time series. What kind of time series? It's sampled at um, it's a very large number of samples in time, right? 16,000 samples per second. This is a typical uh, sampling rate of an audio file. Of course, you go to CD quality, that will be 44.1 kilohertz, means 44,100 samples per second. But this one is 16,000 is something used for in lab settings. This is a good number. So to model such audio files, there is a recent work, not so recent, but let's say 6-7 years ago, called WaveNets. But they are very popular even today. So why they model your audio, raw audio, as time series. And the concept which they use is called dilated causal convolutions. I'll discuss all this in the slides. It's a paper from Google DeepMind, Google Brain, and it was published in 2017, probably 16, 17, maybe. And the reference is here. You can go to this paper on this link. So let's see the concept of dilated causal convolution. So the problem is we have so many samples, 16,000 samples in a second, which is too large. So if you make a one-dimensional convolutional neural network, 1D CNN, this is how it will look like, right? 1D CNN, all of you agree? This is 1D CNN. Is it causal? We discussed the meaning of causal in the last class. Is it causal? What's the meaning of causal? Raise your hand. We didn't discuss last class. Okay, I will discuss now. What is the meaning of causal? Anybody remembers? You remember? Aditya? No? Those who have done signal processing, they will remember. Causal means it depends only on the past or the current input. The current input or past, whatever is available. If you ask me a question today, I only have current data and the past data. I don't have future data. I don't see future, right? So that's the meaning of causal. Causal means it is caused by real factors or in the past. Future cannot cause the past, right? Only past and current or past and present can cause the present or future. That's the meaning of causal. Causal means my uh, let's say probability of pen yn uh, it depends on yn minus 1, yn minus 2, and so on. It cannot depend on yn plus 1. So let's say you are doing real-time processing of audio, right? Your audio can only depend on past, but not on the future. You don't know the future. Okay. So this network is a CNN, convolutional network, 1D CNN, and it is causal, right? My input is a time series, output is also a time series of same resolution. What is the meaning of dilated now? This is dilated. What do you see here? Missing connections. Missing connections. The number of connections here and the number of connections here are same, but the receptive field of this one is much, much larger. Can you see it? The receptive field, what is the meaning of receptive field? The length of the input or the size of the input which output sees. That's much larger than your 1D CNN. Can you appreciate this point? Then we go to the maths of this model. Okay, mathematically, the same figure here. You can say, let's take the point estimate model, not the probabilistic model, but the point estimate. My HT1, 1 is for the hidden layer, first hidden layer. So I have H1 at time t. So my x-axis here is time t, t minus 1, t minus 2, t minus 3, right? And here this is first hidden layer, second hidden layer, third hidden layer, etc. Now my h of the first hidden layer at time t is a function of what? X at time t and x at time t minus 1. And w1 is just the hidden vector, or the weight vector, some parameters. Likewise, my h2, the at time t, which means this node, talking of this about this node. So this node depends on what? H1 at time t and time t minus 2, not 1. And W2 is some hidden vector. Sorry, the weights vector, parametric weight vector. Likewise, H3 is this one, depends on H2 at time t and time t minus 4, right? But can you say my H3 at time t depends on all these x1, x2, sorry, xt, xt minus 1, so on up to xt minus 7? You can say that, right? So that's it. Can you write a general form of HTN in the nth layer? What is HT? General form. Very easy. Almost everybody has done it. Good. So it will be ht in the nth layer is given by is a function of ht in n minus 1th layer and ht minus 2 to the power n minus 1 in the n minus 1th layer, right? And wn is just some parameters. Is that good? Easy? So that is a simple model, but what's the advantage you are getting is you get such a large receptive field with the same number of parameters. How many parameters? What is the size of each W? You see so many W's here. What is the size of each W? Let's take a simple MLP or simple multi-layer perceptron or simple neuron, neural network neuron, which has weights and biases. What is the size of each W? Huh? 2 or 2 plus 1? 3, huh? So 2 weights and 1 bias. So 3. So each W has 3 parameters. Are you convinced? Okay. Now tell me the next answer. For capital L layers, what is the computational complexity of a forward pass? Let's say there are capital L number of hidden layers. Hidden plus output. Let's keep it like that. Capital L number of layers. What is the computational complexity of a forward pass? Forward pass means you are given the X, you want to compute the Y. So just note, I'm not asking about training. Forward pass means just the inference. Given the X, compute Y. Or given the X and the model, compute Y. What is the computational complexity here? Let's say L is the number of layers and let's say um, yes. How will you do that? Okay, whenever you face this question in neural networks, in neural network, what all operations are happening? Summation and multiplication. So inside the hardware, summations are very easy to do. Multiplications take longer. So when we say computational complexity, we generally ignore the number of additions. We only focus on number of multiplications because additions are computationally cheaper, much cheaper than multiplications. So when I ask you what is the computational complexity of forward pass, you should simply compute the number of multiplications happening for a single forward pass. Let's say you want to compute one sample, right? To compute this sample, how many multiplications are required? You can do that. 2 to the power L plus 1. Okay. I got one option 2 to the power L plus 1. Anybody else has some other answer? What's your name? You said Satyam. Okay. To the power L. Anybody else? Yes. Hidden plus output. Hidden plus output. 2L. 2 into L. Okay. 2 to the power L plus 2 to the power L plus 1 minus 2. Huh? Okay. Yeah, generally, when we talk about complexity, we ignore the constants. We only focus on the fastest growing term. So here, if L increases, 2 to the power L will grow the fastest. So even plus 2L minus 2L will not be considered when 2 to the power L is there. But when you say only 2L, In this case, 2 can be ignored, only capital L can be kept because 2 is just a constant. Capital L is the order of growth, linear growth basically, that will be kept. Okay, any other answers? So okay, let's try to do how we do it. Let's say I want to compute this output. So how many computations are involved here? Multiplications are involved here. 1 into 2, 2 here. And here how many are there? 2 into 2, 2 to the power 2. Here how many are involved? 2 to the power 4. Here how many are involved? 2 to the power 8. Total how many are there? 2 plus 2 to the power 2 plus so on plus 2 to the power L. Is that correct? Why? Huh? L layers, Let's say when I go to the first layer, it's 2 to the power 1. The second layer, 2 to the power 2. Third layer, to the power 3. Lth layer, to the power L. What? Oh, I made a mistake. Sorry. Sorry. I was, okay. Sorry. This is correct, huh? Is this correct? I'm counting 4, but they're saying to the power 4. Okay, it's 4 only. Uh, yes, 4 into 2. So, yeah. So, how much is this? This is GP. Sum of a GP is? Huh? To the power L plus 1 minus 1 upon 2 minus 1. Is this correct? Huh? Minus 2? Okay. Okay, to the power L plus 1 minus 2 upon 1. Is that correct? Okay. So when we consider the order, then this 2 term can be ignored. 2 to the power L plus 1 is the final answer. All of you agree with this? All of you agree with this? Yes. Parallelized? No. It's a recurrent model. So basically you cannot make it parallel because you need the previous outputs to compute the next output. A lot of them are not parallel, but they are redundant. They are done multiple times. Let's say when I compute this edge, after some time, this whole frame will move forward. And then to compute this edge, I've already computed it before. So many computations are repeated. They are repeated multiple times. That can be reduced, right? So how do we reduce that? By storing them in our memory. Just store those computations in the memory, and whenever later you need them, retrieve them. Yes, that will reduce our number of computations. Now, assume.
What was the question? To calculate all the complexity up to order to layer L or from layer L1 is 1 to L?
Yeah, I'm coming to that part. Good question. Good point. So now, this is a very good point which Shashank raised. I am not computing one sample. After computing one sample, I move to the next sample. So all those computations which I did for computing the first sample, those I have saved in my memory, and I then move to the next one. I don't have to do all the computations again. I only need to do a few more computations. So if I do it in this fashion, let's say I have already computed everything till t minus 1, means the whole, you can say the whole matrix I have computed. Now I go to t, time t. Now how many computations do I need to do? Huh? I have computed everything till t minus 1, means I outputted a sample at t minus 1. Now I move to the next time step at time t. I want to now output at time t. Now how many new computations I need to do? I can make use of my previous computations. I've saved them in my memory. Huh? How much? Order of L. Exactly how many multiplications? 2L, right? So let's say to compute this node, I need two computations. To compute this node, two computations. 2 is 2 into L. 2L. 2L computations, so order L. So if I do it in a running way, means in a running fashion, my computational complexity is much smaller. It's of the order of 2L only per sample. To output one sample, I need to do only 2L new computations. Right? So this answer will be taken. Okay. Now if I do it in this fashion, what is the storage complexity of a forward pass? What is the storage complexity? I need to store some previous values also, right? So how much storage complexity will be there? Hmm. Pardon? 2 power L. Somebody said 2 to the power L into L minus 1. 2 power L. Okay. Anybody else has any other answer? Okay. So what is the width of this matrix? 2 power L. What is the height of this matrix? L. So you have to store 2 to the power L into L numbers in this matrix, right? Right. But you may now say, okay, this top layer I don't have to store because to compute my tth output, I don't need t minus 1th output of the final output, right? Top layer. So you can say my length is L minus 1, means height is L minus 1. So it becomes L minus 1 into, no, but you're still storing the inputs. So 2 to the power L into L. You're storing the inputs. Okay. So my storage complexity will be 2 to the power L into L. Is this correct? Now somebody may say, okay, now there are some nodes which I don't have to store because they are never being reused. For example, this node will never be reused. These three nodes will never be reused. These how many? 7 nodes will never be reused. So you can save your computational storage by not saving these numbers or by deleting those numbers. How many such numbers will be there? They will be equal to 2 minus 1 plus 2 to the power 2 minus 1 plus 2 to the power 3 minus 1 plus so on 2 to the power L minus 1 minus 1. All right. So, but this sum you reduce from your 2 to the power L into L, but that won't change the order of your computation. So the order will still remain the same, L into 2 to the power L. All right. Was it a good exercise? So now tell me, if I have to generate 1 second of audio, how many computations do I need? To generate 1 second of audio, let's say 16,000 samples, how many computations do I need? Huh? 16,000 into 2L. And L is, let's say, 5 or 7 or something, huh? So it's still a large number. It's still a large number. So generally, WaveNet models, these models, they give very good outputs because they are very efficient and things like that. But still, they are very, very computationally expensive. Very, very expensive as compared to the other methods which use spectrums or spectrograms, right? Compared to them, these are very, very expensive. But the quality wise, they are the best. Means they are, so far, they are very good performance. All right. Any questions so far? Okay, now I just discussed the model. It can be used in different ways. You can use it for analyzing audio or for generating audio, for anything. I just discussed the general model with you. Now, one use case is to generate audio samples. So the original paper, it used WaveNets to generate audio. So which means it is generating a raw audio file, 16,000 samples per second, let's say. Now, PYT is a continuous random variable in this case, right? You can always normalize your audio to lie between, means the amplitudes lie between -1 to +1. Right? That you can always do. So now it's a continuous random variable with values between -1 to +1, right? So now if WaveNet has to generate continuous numbers, uh, its performance is not is basically difficult to generate continuous numbers. So what WaveNet does is it reduces the output space from a continuous space to a discrete space by using how can you make a continuous space into discrete? Quantization, right? You make bins, like you make histogram, right? What is a histogram? A continuous random variable is converted into a discrete random variable, and you make bins, and those bins, the counts in those bins tell you about the distribution. So continuous random variable can be made discrete random variable by quantization or binning. What is quantization? You have a continuous random variable, let's say between -1 to +1. In this case, it's a normal distribution with a mean 0 and standard deviation of 0.1. And I took 1,000 samples from there, and I said, okay, with these 1,000 samples, I want to look at the histogram. And to make the histogram, I used 20 bins. What does that mean? It means my x-axis was split into 20 equal sized intervals, and the number of points falling in every interval, you count them, and it gives you this. And you normalize finally everything so that everything sums up to 1. All right. So let's say in this case there are 1,000 samples, so divide by 1,000, so that's how you get it. Now, if I have to do waveform generation and I divide my space into 20 bins, what is the problem? What is the problem? So I repeat my question. The question is, I want to generate audio. Every sample lies between -1 to +1, and I have uh, quantized everything with bins, equal sized bins, and I trained my model to generate this discrete distribution. What is the problem? My output quality will be very poor. Why will it be poor? I used my best model, very heavy model, to generate these samples, but still my audio quality will be very bad. Normalized in what sense? Some bins have no data and some bins have data, right? So some bins are having so much of data, and all these bins are totally unused, right? That's the problem. This data imbalance leads to inefficiency. Inefficiency means you're asking your model to learn to predict all these bins, but some of these bins are never occurring. So your model, even if it has capacity to learn those outputs, it will never learn because those outputs never exist. So your model is very inefficiently used. And even if your model does it perfectly, it generates the perfect output. But still, when you map your output to the real numbers, it will be very bad because those subtle differences are lost. Are you getting my point? Uh, how do I make it more clear? Let's say in this class, I take age from, in this class, people in this class can be of age from 0 years to 100 years, right? And make 100 bins and put people in the bins. What will you get? Almost all bins will be empty. From 0 to 17 probably will be totally empty. From 17 to 25 or 24, you may get so many samples, and after 24 again empty. Maybe I'm there, so one somewhere. And so that's it, right? So which means all your other bins are totally unused, and within those bins, uh, my distinction is lost, whether you are uh, 20 years and 1 month or 20 years and 2 months. Everybody's in the same bin. Distinction is lost. On the other hand, if I would have said, okay, take bins from 17 years to 25 years and now make 100 bins, you are preserving those fine differences also. Let's say 1 month difference between two people's age, even those are preserved. Something like that, right? In audio also. So if my distribution is something like this and I'm making uniform bins, it's totally useless. It's very inefficient. So we take some ideas from, how many of us, how many of you have studied coding theory? No? Okay, maybe information theory you can study later. I'm just telling some line. If you don't understand it, don't worry. It's so maximum coding efficiency if entropy of bins is maximum, which means if all the bins are more or less filled, and ideally if all bins are filled with equal number of samples, then you will get the best efficiency, coding efficiency. So how do we do it? Anybody has any idea? If I give you 1,000 samples and I ask you make bins in such a way that all bins are filled equally, means divide your x-axis in such a way, it could be non-uniform, means non-equal intervals also, but make your intervals in such a way that all intervals are equally filled. Huh? Logarithmic scale. If you take a logarithmic scale, what do you do with the negative numbers? Log of negative number is not defined. I appreciate your idea. Your thought process is very good. Take logarithm because logarithm will like spread it in such a way that these ones get high resolution, these ones get low resolution. I appreciate that idea. Think a bit more. How will you achieve it in practice? Direction is correct, but refine it. More answers? Yes, that's a very good answer. Make your bin size inversely proportional to the PDF height or the likelihood. That's a very good idea. Practically, how will you do it? Can you write the algorithm to do it? Direction is good, but refine it and make your final algorithm. Good answers. Both are good answers. Any more answers? Any more answers? Yeah, good answer. Good answer. That you do it iteratively. Any more answers? Okay. Let's say I'll give you a very simple answer, very you will understand it hopefully. Uh, all of you sitting in this class, let's say, are from age 18 to 25 years or 70 to 25 years, right? And I want to make 20 bins, let's say 20 bins to divide the age, right? Let's say, assume I have a large enough class which represents the distribution of any typical scenario. Huh? How many students are there? Let's say 40. I will first of all sort you based on your age, right? Starting from, let's say, somebody is uh, 18 years and 5 months. Okay, sit here. 18 years and 5 months and 3 days. Okay, sit here. Like that. Sort, first of all, based on age. Now, you're 40 of you. I want to make 20 bins. Now make pair of two people, right? And now this pair defines my interval, right? You get it? Let's say these are my pairs. Put boundaries like this. And these values, then I can preserve. And I will say these values are, any new person comes, that person will basically follow these values to enter a bin. Uh, it could be a little heuristic. Let's say in this case, if it is, it's very sparse data. So you can take this one and take their mean, something of that sort, right? It's a bit approximation involved here. All right, good strategy, and you will get equally filled bins, right? Assuming that your distribution represents the correct PDF, correct, your samples represent the correct distribution. This is one way. Now, can you do mathematically more precise? So this is how. So what I explained now, the algorithm, it actually comes from a very good mathematical theory, which I will discuss now. Uh, Instead of sampling YT uniformly, you find out the CDF and sample the CDF uniformly, and then take its projection on Y. Those are your bins. So what is f of Y? It's the CDF, cumulative distribution function of Y, and it is defined in this way. All right. Does that make sense? So let's say if your age is 18 years and 3 months, so you are the youngest one here. So value of CDF for Y less than 18 years, 3 months will be always 0. And as soon as it hits you, it will increase by how much? 1 by 40. Next person is 18 years, 5 months and 3 days, something of that sort. And then the CDF will, at this point, it will increase further by 1 by 40. So it becomes, value becomes 2 by 40. In this way, it keeps increasing, and you get a CDF. I will just tell with another example. Let's say this is your distribution around 0, between -1 to +1. And as your points are here, the bins are very unequal distributed, but if you plot the CDF, it will grow like this. Now you uniformly make bins in your F on the F axis and take its projections onto the Y axis. So what you get here is very large intervals here, but then very fine intervals here, very fine intervals here, and then again large intervals here. All of you agree with that? Right? So let's say if I take equal bins, let's say 25, 50, and 75. And you look at the bins. So you see one very large bin, small bin, very large bin. They are not of equal size, but they are equally distributed. Okay, that's the idea. So this is the procedure now. Given the samples yi, first of all, estimate fy. How do you estimate fy from the samples? From PDF, you know how to do it, integrate. From samples, how do you do it? This is the procedure. First sort them, first sort all of them, and then you keep increasing by 1 upon n every time you meet somebody. Increase by 1 upon n. That's how you estimate f. That's how I did it programmatically, and that's what I got. Now you bin your f-axis, the y-axis, into capital B bins. You can choose whatever capital B you want. We took 20. And these you from here you get the endpoints of your bin. One endpoint is 0, one is 1, and in between there are 19 more endpoints. And then project them back to get your y tilde b, which are your endpoints of your interval. Clear? Easy? Now equivalently, you can transform your y to another variable fy that has close to uniform distribution. Transformation of random variable. Same thing. If this small f is equal to capital F, then your capital Fy will lie between 0 and 1. Same thing happens. All right. Is this point clear? Now, how WaveNet does it? WaveNet uses, basically you take large number of speech files, look at their samples, look at their PDF, and you approximate it with some simple PDF. So they found that this was a very old paper in 1970s, probably. And they found that if you use this kind of a transformation, it roughly maps, matches your CDF of y. I mean, this when you plot this, it lies between -1 to +1, but when you scale it appropriately, it approximates the CDF. Yeah, it roughly maps to the CDF. And if you start it from 0 to 1, this is roughly the CDF of speech samples typically. And they approximated it with a very simple to compute form so that any new sample can come. You simply compute f and then put it in an appropriate bin. Is that clear? This is called mu law compounding transformation. Here mu can take any value, any positive value. That's how it does. By controlling mu, you can control the width of the order curve. All right. Okay, now quickly, residual and skip connection. If you look at that paper, oh, first of all, read that paper, WaveNet paper. I've put it in the readings folder, WaveNet paper. So you will see here, there many terms are used like residual connections, skip connections. So they basically mean that you do some, let's say, your X becomes H, H again becomes Y or something. And then your Y is not simply a function of H, but it also you add X into it. Your Y is a function of H plus X. So that is called the residual connection. You can see here. You can see here, this is getting added as it is here, so that you don't miss any information. And similarly here, skip connections are basically, just read about it. It's very easy concept. Skip connection basically means you are skipping the entire block. Let's say multiple blocks you are skipping. It's like residual connection, but you are skipping now large number of blocks, not just layers, but even blocks you are skipping. So that's the architecture. These are easy to understand things, so I'm not, and also mathematically not very challenging. Now, the next concept here is the conditioning of the network. You don't want network to output just random things. You want to condition it on some input, on something, let's say. Okay, the example which WaveNet deals with is, let's say I give you the words. These are the words you have to speak. Let's say I am giving this talk. I give you the words. Now I want it in the voice of a old man, or a young woman, or a male baby, or male child, something of that sort, right? So you can condition it on some global conditions. How do you do that? Just make your um, let's say you had three layers. Now let's say, just to understand, this is your x, this is your h, this is your y. So your h is a function of x, but make it also a function of some condition c. Give c also as an input to your layer, so that now h is a function of x as well as the condition c. And this condition c could be of two types. Okay, I have used the notation h here. So your y depends on h, but y also depends on x. Let's say your y depends on x, but it also depends on some conditions c or h. Now your h can be constant for all the entire audio. Let's say if I say it's a female, young female voice, then it is constant for the entire audio. Or I could even make it local conditioning, which means it changes with time. Let's say I give pitch contour as an input. I say, I want a musical sound. Huh? Don't say I'm giving this talk, but sing it in this pitch contour. I am giving this talk, like that, right? So what are you doing? You're conditioning it on a pitch contour or melody contour. And this melody contour also changes with time. It's not a global condition, but a local condition. So that's how you do it, local conditioning and global conditioning. Easy to understand. So these are the things which you will encounter when you read this paper. These are mostly the concepts. What the paper does. In the paper, they are trying to generate audio. Let's say one use case could be TTS. I am giving this talk and you want to generate the audio corresponding to this text. So first of all, they use some existing methods to convert this text into a time series or sequence of features. Let's say my MFCC features, or could be any, you read the source filter model, right? So source filter parameters at every time instant or every sample. And then they give this as an input to the WaveNet. And then the WaveNet generates the final raw audio waveform. Right? So it's not from text directly. WaveNet does not convert text to speech. It converts text to some features, and then which are temporal features at sample level, and then from there it converts to waveform. How do they evaluate? There is no mathematical way to evaluate the quality of audio. There is no mathematical way to do that, or there is no model to evaluate it. You can make a model, let's say an ASR model, and measure the accuracy of your ASR model, but the to check the naturalness of the sound or of the voice, people do subjective tests. You make 100 people listen to the audio and tell how natural the audio sounds like, and they give a score between 0 to 5, and then take the mean of all those scores. That becomes a score for that model. So it's a tedious method of evaluation. It's not as simple as finding F1 score or accuracy. So further reading, read the WaveNet paper. There is a nice appendix A where they discuss text-to-speech theory, little bit, 1 page, I think. Read that. And then another method which we may discuss it in the next class also, about temporal convolution networks for action segmentation and detection. They also use dilated convolutions for videos. Thank you very much.